Okay, so at this point, of course, you can now type your name into the chat. Anything that you type from now on, I'll have a record of for your attendance. Anything from beforehand, I won't have a record of yet. So, all right, so welcome again. Thank you all for coming. It's been a while since we had our last session, so I want to just recall that last time we talked about differentiation, and today we're going to talk about integration, and this is going to complete the kind of mini calculus workshop. Maybe before we get started with math, I mentioned this last time, but I want to say it again that I'm going instead of what I've usually done for the certificates, which is I've usually just asked everybody to send their name and then I try to make sure that I don't have any mistakes. What I'm going to do this year is I am going to send you a full list of the names to be certificated. And then if you don't see your name on that list, or if I've made a mistake with your name on that list, then you can send me a message telling me to put your name on the list or telling me any correction with the spelling. And that way I'll have all the names already by the end of the class, and hopefully the certificates will get to Liberia much closer to the end of the class rather than just starting the process on the last day of class. So I'm going to try to start that process this week. I'll send out a list of names to the WhatsApp chat and everybody can verify. I think it's fine because there's not going to be anybody new in the next month. So everybody who's going to get a certificate is somebody whose name I already have. So I'm going to send that out this week. Not the difference. I'm not going to be separating it yet. Distinction, participation, completion. I'm just going to send one list of names for anybody who's going to get some certificate, and I'll ask for any corrections so that way I can maybe make the certificates and have them printed out before the end of the workshop. And so then Mr. Randolph will find someone to carry them to Liberia, and they should get there earlier than they would otherwise get there. Okay, so more on that this week. I'll send a message to the chat this week, and just look out for that in your WhatsApp. Okay, thank you. So again, you can type your name now if you want to be recorded for data for attendance. And let's get started. Okay, so let's try to remember. It was a long time ago, but last week, what did we do? It wasn't last week, I guess. I shouldn't say last week, last session. So last session, we discussed differentiation, and this session, we're going to discuss integration. And so thank you again. I don't remember who it was. I think it was Manfred Molba who sent me the grade 12 high school textbook, in particular, the part that deals with integration. So I was able to look at this to see, what about integration are we expecting a high school student to learn in a small calculus unit at the end of a high school math curriculum. And so the main topics that are covered in this textbook are, the definition of an antiderivative or an indefinite integral, some basic rules for computing antiderivatives, the definite integral, what that means, the fundamental theorem of calculus, some basic rules for computing definite integrals, and last, approximating the area under a curve. And so this material is covered in four sections of this chapter 22 of the book. So 22.5, 22.6, 22.7, and 22.8. And let me just get the page numbers there. I think that's pages 577 up through 592 of the book. Okay, so it's not a large unit. It's only 15 pages, and a lot of those pages are just taken up with many exercises and examples, which is good. Okay, so this is the reference, and this was sent out to the chat. If anybody wants me to send out a copy of the book, I can send it again. But this, I think, was sent out. Let me try to find it. This was sent out on March 16th. Okay, so Manfred Molba sent this on March 16th. So I'll just write that here. Manfred Molba sent soft copy of textbook to the WhatsApp chat on March 16th. Okay, so if you wanna look and find where that is. Okay. So these are the pages that have this material on integration. And so, how do we do a workshop on integration, especially a short workshop? I mean, integration is a very, very big field. You certainly can't cover all of it in one day, but we only have one day for it. So, what do we focus on for a day? And to some extent, the good news here is that, unlike in the case of differentiation, most of the important material, at least the important material that's in that textbook, we can cover here in one workshop meeting because it's less so there isn't as much to know from the textbook here compared to differentiation. Differentiation has a lot of motivation, a lot of geometric interpretations, and then a lot of different formulas. The amount of integration that the textbook covers is just not that much. So we will be able to touch on almost everything in one workshop meeting here. So, some good and bad things, in my opinion, at least, about the textbook. So, the best thing about the textbook is it has lots of practice problems and lots of worked examples. So, it's very easy to get a lot of practice by doing all of the textbook exercises, and not just the exercises, but also they work out lots of examples step by step. So, you can really see how everything is done. Um, Now, I do feel that the textbook has a little bit of a shortcoming, and that's that I don't think it gives adequate coverage to the meaning of the definite integral and the fundamental theorem of calculus. Okay, and what I mean by that is that I think if you haven't taken a university course in calculus and you're expected to teach this unit and you only have this textbook as a resource, then I think it's not going to be very easy to explain why integration works if a student is asking, okay, so why does this work? Right? I mean, if you look through these pages of the textbook, they talk about computing antiderivatives, then they talk about computing definite integrals via antiderivatives. They then talk about approximating areas by rectangles, but it's not really linked to anything else that's done in the course. And then in particular, they say things like the fundamental theorem of calculus is that the definite integral from a to b of f of x dx is equal to big F of b minus big F of a, where big F is an antiderivative of little f. I mean, that is the fundamental theorem of calculus, but they don't tell you what the definite integral means in the first place. They're stating it like it's a definition when it's actually a theorem. So I think it's very easy to get confused in this case of like, what's a definition? What's a theorem? Why does anything work? Why do you have this magic? What's the link between definite integrals and areas under curves? Why does taking an antiderivative magically relate to areas somehow? So I think it's good to make sure that anybody who's going to be teaching this material at least has some sense of what's going. You're not seeing anything in Moscow. Are other people seeing the screen? The screen should be shown. I see it on Zoom. Are people seeing the screen? Yes.
Yeah, I've seen the stream.
Okay. All right. Moscow, maybe you want to log out and log in again. I think it's something on your end. Okay, it's being broadcast. So, okay, so if you're teaching this stuff, I'm not saying that you need to be able to prove the fundamental theorem of calculus, giving a rigorous proof, but it's good to have some sense of why something like this could possibly work. Why is it not total magic? Why can you calculate areas by taking antiderivatives, right? I mean, areas and antiderivatives are two completely different things. Why do they give the same results? Okay. So, and I think this is particularly for this textbook, I think this is in very big contrast to the meaning of the derivative, which I think the textbook does a very good job at. So the textbook has a nice diagram and it shows how secant lines become tangent lines in the limit and how that limit gives you a formula for the derivative involving limits, and then showing how there's actually shortcut formulas for certain functions that evaluate that limit. So I think the book does a pretty good job with what is the meaning of the derivative? What is it supposed to symbolize? I think it does not do as good a job about the meaning of the integral. And that's, maybe to be expected. Integrals are a little bit more complicated than derivatives. But I think for a one-day workshop, of course, we're not going to be able to go and, talk about every single integration formula. But what I do hope to be able to do is spend some time talking about the meaning of the fundamental theorem of calculus and what an integral is. And this is especially, I guess I want to say, for a workshop with this group, most of whom spent an entire year doing a calculus workshop with me last year. Okay, so we're not starting from nothing. We're starting from some background in calculus. But I think it's pretty important that a teacher who's teaching calculus or who's teaching the calculus unit of the grade 12 curriculum is not just stating formulas that they have no idea why they work. Okay, it's good to understand something. Okay. So so, what does this mean in a little bit more detail? Okay, I'm not going to give a proof of the fundamental theorem of calculus. A rigorous proof really belongs to that part of math, which would be called real analysis or mathematical analysis. And that's well beyond a reasonable high school course. It's not something that I would expect people to be able to know. But if you look at the textbook, it just starts computing lots of antiderivatives. And it's like, well, we already know why it's useful to compute a derivative. A derivative is useful because it tells us a slope of a tangent line, it tells us a rate of change, it tells us lots of things in physics. It tells us, if you remember from last year, it tells us how to do optimization problems, how to maximize and minimize things. So I think before we just start saying, okay, let's compute loads of antiderivatives, it's good to have some sense of why this could be a useful thing. Okay. And so if in the future you find yourself running a calculus workshop for your local teachers who are teaching this material, you may decide that it's worth it to discuss the computations first and the ideas second. And maybe also if you're teaching a class, it makes sense to warm people up with the computations. They're less confusing. Students know how to do them. And then maybe afterward you can tell them why you're doing these computations, what the ideas are behind them. But for me, for this workshop audience, again, most of you have already been through a long calculus workshop for a year. I want to start with the ideas before I go to the computations. Okay, so before we just start computing lots of antiderivatives, I want to spend a little bit more time on the ideas. And the ideas distilled at a level which I think can be understood by a high school student. Okay, so that will be useful for teaching. Okay, so this is kind of how I was thinking about doing doing this doing today's workshop. Okay, so let me just recall, what's the whole idea with integration. So what is the spin? Last time we talked about the odometer problem. Now I'm going to talk about the speedometer problem. So suppose a car is driving in a straight line and we're sitting inside and we're watching the speedometer. It's telling us how fast we're going. And the question is, can we determine how far the car has traveled? And now again, if the car goes at constant speed, this is easy, right? Because all we have to do is we have time on the horizontal axis. I can have speed on the vertical axis. And if the car is going at constant speed, that means I have that means I have a horizontal line here up to a certain amount of time. Maybe I'll call this t. And if I travel at a constant speed for a certain amount of time t, the total distance traveled is just going to be the area of this rectangle, right? Area equals distance. Right? The area here is equal to the distance traveled. And that's just because we have the standard pre-calculus equation, distance equals speed times time, right? And this rectangle over here, this the length of the rectangle, this is the time, and the height of the rectangle, this is the speed. Okay. So the area of this rectangle is exactly the speed times the time, and so this tells us the amount of distance traveled. Okay, so if I watch a car speedometer and we're traveling at 30 miles per hour the entire time, and I watch it and we drive for an hour, then I know that we've gone 30 miles, right? 30 miles per hour times 1 hour is 30 miles. Okay, so this is very, very basic, does not require any calculus. All right. Okay. Any questions on this? Okay, this should, I hope, be pretty clear, right? Okay, but in real life, we don't drive at constant speed. We slow down, we speed up. Different roads have different speeds. You might have to wait in traffic. You might have to wait for a traffic light. All sorts of reasons why speeds might change. Okay, so what happens if the car speeds up and slows down? Well, let me just go back to this old graph here, right? This is my speed. Here it's constant. But if I imagine that I started at this speed and then at some point I got faster and then I got slower, it seems pretty reasonable that even no matter how fast or slow I go, that the total area under that curve is going to represent the amount of distance that I'm driving. So just like when the speed is constant, the area under the line represents the distance that I traveled. Also, when the speed is not constant, the area is going to represent the distance, right? The speed is when the speed is higher, right? That means I'm covering more distance faster. So it makes sense that with higher speed, I cover more distance. With lower speed, I cover less distance. And with constant speed, I just cover that much distance. Okay, so I mean, the reason I'm telling you that I'm not going to quote unquote prove the fundamental theorem of calculus is that I'm asking you to accept this on intuition, that if I draw the graph of my speed, then the total distance traveled is going to be the area under that graph. Okay, so let me draw this in a picture. So what happens if the car speeds up and slows down? I'm going to make another graph. So again, this is my time axis. This is my speed axis. Maybe I'm even going to start at some time A, be a little suggestive for integration. So I'm going to start at some time A and I'm going to finish at some time B. And maybe this is my speed, and then maybe I speed up a little bit, and then I slow down, and then maybe I come back to a constant time here. And so what I want you to accept is if I draw the lines at time A and equals B, then this area here is equal to the distance traveled from time A to, sorry, time, I'll put it as a lowercase, from time A to time B. Maybe I'll write it here, time A to time B. Okay. So I think this is believable, right? The higher your speed is, the more distance you're covering at any given time. The lower your speed is, the less distance you're covering at any time. If I stayed at a constant speed, this is definitely the area. So if I speed up a little bit, I'll get a little more area. If I slow down a little bit, I'll get a little less area. So it seems very, plausible, and it is in fact true, that the area under this curve from your start time to your end time, we'll call those A and B, the area under your speed curve is equal to the distance traveled. So let me write that in words. So area under the speed curve is, again, assuming you're traveling in a straight line, equals the distance traveled. Okay, so already with this insight, we're getting some idea of what does antiderivatives have to do with area, right? If area is representing a distance, then you have distance and speed. There's a derivative relationship there, so maybe from speed back to distance should be an antiderivative relationship. So we're already starting to see kind of why antiderivatives might have something to do with areas. Okay. But for now, we're not there yet. I haven't said the word, I haven't done any I haven't talked about derivatives or antiderivatives or anything. For now, we're just saying I'm drawing a graph of the speedometer. I'm watching the speedometer, which means I can draw this graph over time. And look, the area under this should represent the amount of distance that I've gone. Okay, we haven't done any calculus. We haven't taken any derivatives or antiderivatives. I'm just saying this area should be the distance. Okay, so before I move on from this, any questions here?
Hello?
Yes, question,
Yeah,
Prince?
Prince.
Yeah.
Yeah, I have a question. So that means on this speed, if to calculate the area will be equal to the distance from the which we gave previously, which is about time uh, times will be equal to the distance from now, right? If you are asked to calculate the area, will be equal to the distance from now, right?
Yeah, it's the distance from time A to time B. So you imagine you're starting at time A. This is a speed versus time graph, right? This is
Okay, yeah. So that's
right.
my question. So the area will be equal to the speed times the time.
Well, okay,
Is that
right?
what?
In the previous case, right? So when your speed is constant, the area is equal to the speed, the distance is the speed times the time. But
Okay.
when your speed is not constant, your speed is changing. So you can't say speed times time because the speed isn't just one number. You're getting slower and you're going faster. So you have to figure out some way of calculating your distance even when your speed is not constant. And that's what this is where calculus comes in. So speed is constant. That corresponds to your speed curve just being a horizontal line. That's a constant. In that case, you got speed times time. That's equal to your distance. So what I'm saying is that the generalization of this to the case where your speed is not constant is going to be, well, I can't just say speed times time because speed is not a number anymore. It's a function. So what you do get though is that the total distance, just like in this previous case, same analogy to the previous case. In this case, the distance was the area under the speed curve. And in this case, the distance is also the area under the speed curve. So so speed times time, that's hard to generalize when speed is not constant. But area under the speed curve, that generalizes just fine. The area under the
Oh,
speed curve makes just as much sense in this situation as it does in this situation. Okay, so in both cases, that area is giving you the distance traveled. Is that okay?
yeah, yeah. Thank you. Thank you so
Great.
much, sir.
You're welcome. Other questions? Okay. So what happens here? So this is something to recall from the derivative unit. So let's say that we were asked to plot the total distance traveled against time. So if I let, for instance, s of t be the function that's that's defined by definition. Oh, sorry. Oh, why does this keep happening? By definition, I'm going to let s of t be the distance traveled up to time t. Okay. So exactly right. So this is exactly. Thank you, James. Yeah. So what you've written there is exactly right. So everybody can read James' comment for extra clarification. Okay. So if I'm going to let s of t be the distance traveled up to time t, okay, this is going to be a function. So remember what the derivative means, then, well, the derivative s prime of t, remember what this is. This is the instantaneous rate of change of s at time t. If you recall what a derivative means, it means a rate of change. It's an instantaneous rate of change. If we were drawing it, it would be the slope of the graph of s of t. I'll have a maybe a little graph here to show you, right? I mean, so if this was, s of t, this is time, and now we have a different unit on our axis. This is now the distance axis. If this is, s of t, if this is the graph, y equals s of t, then if I look over here, the derivative, remember, represents the slope of a tangent line, right? And the slope here, so at some point t, the slope is equal to s prime of t, right? That's what the derivative is. Okay, so S prime of t is the instantaneous rate of change of the distance at time t. So how fast is distance changing with respect to time? But we have another word for this. When we talk about the rate of change of distance, or what's the same thing as the rate of change of position, that has a name in physics. That name is speed or velocity, right? So, but also, well, I won't say also, maybe I'll just say observe. This is the same as the velocity. And when I say velocity, I really just mean speed. We're assuming we're driving just in a straight line in one direction. Speed at time t. Okay? So if we make a function s, which is our distance traveled function, then the derivative of s tells us the speed, right? Because how fast is our distance changing? Well, the slope of the distance is exactly your speed. The slope of your distance, remember, if it was a straight line, that would just be distance divided by time. That's exactly speed, is the slope. And in general, if it's a curved line, what we do is we take the slope of the tangent line. And that gives us instantaneously, it gives us distance divided by time. So if s of t represents your distance, then its derivative represents your speed. This is a standard physics formula, but it also just makes sense because a derivative means a rate of change, and rate of change of distance is speed. That's exactly what speed is, right? Exactly. Okay. So, all right. So we've got two things going on here. We've got, if I draw the speed curve, then the area underneath is the distance. If instead I draw the distance curve, distance versus time, then the slope of that is the speed. So what we're going to do on the next slide is that we're going to put these two ideas together, and then the fundamental theorem of calculus is just going to come out from this. Okay? So, and when I say the fundamental theorem of calculus, what I mean is our method for how we're going to calculate the area under a curve. So, but before I do that, I want to make sure that everybody's on the same page here. That if I make a function which is by definition the distance, then the derivative of that function is going to be the speed. So, are there questions on that? When I say this, I mean, of course, this. This is basically what we talked about last time. This was the odometer problem. If you know your distance function, how do you figure out your speed? And that was the whole point of last workshop, was that to do that, you need to be able to calculate the slope of this tangent line. That's the derivative. This is the, what motivates calculus from the beginning. Okay, so we've got these two ideas. Okay, so now let's show why the fundamental theorem of calculus works. Okay, so this is a dense slide, but we're going to go through it slowly. Okay, so I've broken it up into 9 points with numbers, and each point is very small, and we're going to put them together and it's all going to work well. But I'm going to go through it very, very slowly. So I'll try to make it slightly bigger. You're looking on your phone. Okay, so the first thing is just what I just said, that the derivative of the total distance traveled function, if we call that s of t, is going to be the speed function, which we call f of t. So f here, I'm naming it. So s is distance and f is speed. So a little bit inconvenient because s is the first letter in speed, but for us, we're gonna call f to be the speed and s to be the distance. Okay. So the derivative of the distance function is the speed function. What that means, in other words, that's just saying that the distance function is an antiderivative of the speed function. What does antiderivative mean? It just means inverting derivative. So if f is the derivative of s, that's just the same thing as saying that s is an antiderivative of f. By definition, an antiderivative just means some function that when you take the derivative, you get back to f. So an antiderivative of f is just some function s, so that when you take its derivative, you get f. So these first 2 points, we haven't done anything. Point one is exactly what we had on the previous slide. And point two here is saying that the function s is an antiderivative of f. Okay, great. Okay, so now point three, also going to be a pretty easy claim. So if our car starts at time A and travels until time B, and its speed function is f of t, then the total distance traveled is exactly s of b, right? Because s is the distance function, and we want to know how long it's s of t is the distance it travels up until time t. And so if it's going to go up until time b, then s of b is the distance it travels up until time b. Okay? So this s of b over here represents the total distance traveled. Okay? So I don't want to move. We're going to do this in three groups of three because we've got 9 points. So before I move on, questions about steps one, two, and three. Do you believe me over here? Is there anything that you don't like? Completely ignore the rest of the slide for now. Let's just talk about parts one, two, and three. Are one, two, and three okay for you? Okay. All right. So one, two, and three are fine. So this S of B is giving us the distance traveled. So what does that mean? That means that the area under the curve is S of B. Remember, the area under the curve is the distance traveled. So this area is exactly this S of B. That's the total distance traveled. And what is S? Well, it's some antiderivative of F. Which antiderivative is it? That's what we're going to worry about in the next 5 points over here. But the area under the curve, remember, the total distance traveled here is the same thing as the area under the curve. That's what I asked you to accept earlier on. So the total distance traveled is the area under the curve, just like in the constant speed case. So the area under the curve is S of B for some antiderivative S of F. Now, what's S of A? Well, S of A is just zero, right? Because the car starts at time A and finishes at time B. So at time A, how much distance has it gone? Well, it just started, so it hasn't gone any distance at all, right? So our total distance traveled function is S of t, and that means if I punch in A for that function, that's exactly the start time. So at time A, the car hasn't gone at all. So that means that S of A is just going to be zero here. Okay, so 0.5, this is not so bad, right? At S of A, car hasn't gone at all. Okay, now let's do 0.6. So now here's a claim that if f is any antiderivative of f, if big F is an antiderivative of little f, then, well, we know that little s of t is an antiderivative of little f. So if I have any other antiderivative, that means I've got two different functions and their derivatives are both little f. And if I have two functions with the same derivative, then they have to differ by a constant. Okay, this is a basic thing with anti-differentiation with integration. If you've got two functions that have the same derivative, meaning they've got the same rate of change everywhere, then the only thing that can be different about them is where they start, right? These two functions have the same rate of change everywhere. Well, maybe they differ by a constant, but once they differ by a constant at one place, they're going to just have the same rate of change everywhere, which means they've got to just differ by that same constant everywhere. So if I have two functions that are both antiderivatives of little f, then one of them has to just be the other one plus a constant, right? So maybe I'll write this here that these are both antiderivatives of little f of t. Okay, so if I take any antiderivative at all, f of t, well, it's got to be equal to my specific antiderivative. This is the total distance traveled function, and then plus some constant, which I'm not telling you yet what this constant is. Okay, and then I can just move the c to the other side of the equation. So another way of writing this would be that f of t minus c is equal to s of t. So f is just some arbitrary antiderivative, and s is the specific antiderivative that gives me the total distance traveled. So I think 6 is maybe the first hard thing that we've done. 1, 2, 3, 4, and 5 are all pretty basic, right? 6 is the first time where you need to actually be like, okay, hold on, I've got a lot of letters floating around. What's going on here? So let me take a pause after point 6 and ask if anybody has any questions on parts claims 1, 2, 3, 4, 5, or 6 here. Okay, no questions. All right, so now let's finish up. Let's do 7, 8, and 9. So I want to figure out what this C is. I want to know what C is. So what I'm gonna do is I'm gonna plug in my start time A on both sides. So if I plug in A on both sides, f of t just becomes f of A. C is just a constant, stays as C, and S of t becomes S of A. So I get that f of A minus C equals S of A. But S of A we already saw was 0, right? S of A just means how much distance have you traveled at time A. You haven't started yet, so that's equal to 0. So this tells us actually that f of A minus C is equal to 0, and that allows us to solve for C, right? If f of A minus C equals 0, that means that C equals f of A. So I'm going to write a comment here. I'm going to say we've solved for C. Okay, it's going to be equal to f of A. Okay, so now what happens here? Let me go. We have that f of t minus c equals s of t. If I now plug in b over here, if I plug in b, I get f of b minus c equals f of b equals s of b. But c we've already decided is f of a. So by plugging in b over here, we get that s of b is equal to f of b minus c, or in other words, f of b minus f of a. So maybe I'll write an extra note here is plug in b for t in, I guess, in 6. Okay, we plug in b for t in 6. And that gives us that this S of b, the total distance traveled at time b, is equal to f of b minus f of a for any antiderivative big F of little f. But hold on, we already saw here in point 4 that what is this S of b? That's the area under the curve, right? It's the total distance traveled is the area under the curve is S of b. So instead of saying that S of b is equal to f of b minus f of a, we can say that the area under the curve, so the area under the graph of f of t from t equals a to t equals b, is exactly f of b minus f of a. And this is the fundamental theorem of calculus. Okay? So this is my kind of non-proof derivation of the fundamental theorem of calculus. Okay, so this, if you go through these steps slowly and seeing this the first time, you may have to review it. It's fine. It might take reviewing it 5 times or 10 times before it makes sense. That's okay. But every single step is here. And in the end, you can, once you understand it, you can convince yourself that this really makes sense. This is the fundamental theorem of calculus, okay? We're saying that the area under the graph of a speed curve is equal to f of b minus f of a for any antiderivative big F of little f, any function big F whose derivative is little f. Okay? So that is the relationship between antiderivatives and areas. But it really comes from, I mean, all of the ideas. This is just like equations and algebra and plugging in and manipulating. The idea is just that the distance function is an antiderivative of the speed function. And distance is the same thing as area. So once you know that, then you understand what antiderivatives have to do with area. Distance is antiderivative of speed, and distance can be graph, distance can be shown, can be visually modeled by an area under a curve. Okay? So once you have those two ideas, then it makes sense that the area under a curve should have something to do with antiderivatives because distance is an antiderivative of speed. Okay, so this is my kind of non-rigorous derivation of the meaning of the fundamental theorem of calculus, which maybe I'll state over here and then I'll go back. I'll say, what is the fundamental theorem of calculus? If f of x is a continuous function on some closed interval a, b, with f of x greater than or equal to 0, then the area under the graph of f of x between x equals a and x equals b is exactly f of b minus f of a for any antiderivative big F of little f. So when I say the area under the graph of f of x, I mean, of course, also above the x-axis. Okay, so as a picture, what I mean is exactly this. It's exactly the same picture I've shown. If I have a and I have b, and this is my function, y equals f of x, then by the area under the graph, I mean this area. Okay. So if this is my function, y equals f of x. Okay, so this is the fundamental theorem of calculus. And if we want to say loose language, we say that the derivative of the area under the graph of f of x function is f of x itself, which means the antiderivative of f of x gives the area under the graph. This is loose language. On the previous page, it's done somewhat more precisely. Okay, so the way we calculate the area under a graph is by finding an antiderivative, finding some function whose derivative is f, and then just calculating f of b minus f of a. Okay, and this is the fundamental theorem of calculus because it turns something that's very difficult, finding an area of a curved figure. This is not something that's straightforward to do. It's not a geometric polygon. This could be some arbitrary curve. And it says actually to compute this, all you need to do is find an antiderivative and then plug in some numbers. And often, as we'll see in a few examples, finding an antiderivative is not always that hard. And it often will be quite easy. Okay, so let me just go back to this slide. I didn't give a chance. Does anybody want to ask any questions on this slide? And just remember that if the whole thing is not completely clear, that's okay, as long as you think you can look at it, and if you spend more time thinking about it, it will become clear. But if something is something that you think will never become clear, then it's good to ask a question about it now. Yeah. All right. Any questions? Okay, if there's no questions, and thank you, James, for providing the summary. So that's a summary of this slide over here. Okay, simplifying the concept by, doing this in loose language without all the equations. Okay. Okay. So this is, I think, at this level, if you're teaching anybody integration, it's good to understand it at this level. I think it's not maybe necessary to understand it at a deeper level, at least to do a basic calculus unit, but it's good to understand it at this level rather than just say, oh, how do you calculate this? Oh, take some antiderivatives and punch in some numbers. I think without any context, that just seems like total magic. Why would that work at all? Okay. So this is what lets it work. Okay, so let's actually do some antiderivatives. Now we see, okay, why is it useful to calculate antiderivatives? Well, it's useful because it helps us figure out areas under graphs. Okay, so let's do some antiderivatives. We've got a one-day integration workshop, so we have some motivations. So let me just give the definition. So if you have two functions, little f and big F, and these are functions where the derivative of big F is equal to little f, then big F is called an antiderivative, not over, sorry, an antiderivative of little f. And the process of finding an antiderivative is called either antidifferentiation or integration. And the notation we use is this. We write, and this is read, the integral of f of x dx is equal to capital F of x plus c. So maybe I should clarify what some of these squiggles mean, right? So first we have this. This symbol is called an indefinite integral. So over here, this is what's sometimes called the integral sign. So this is the integral sign. This dx here is what's called a differential. I think at this level, it's not very important to say what it really means. It's just, you should think of it as just part of the notation. Okay. Eventually, it will become important when you're doing use substitution and trig substitution and changes of variables and all sorts of stuff. But for our purposes today, this dx is just part of the notation. When you want to say the antiderivative of f of x, the notation that you use is integral of f of x dx. This is just what you write. Okay. And then what is that equal to? Well, it's equal to the antiderivative. And then we also always say this plus c, right? This plus c here is an arbitrary constant. Right, we have an arbitrary constant over here. And what's an arbitrary constant? The point is what we said before. If capital F, if you take its derivative to get little f, well, if you just add some constant to it, that's never going to change the derivative, right? If I have some function and I add 5 to it, that just moves the graph of the function up by 5 units. It doesn't change the slopes of any tangent lines, right? It just moves the graph up. Or if you want to think about it algebraically, if you take a function and if the derivative of a constant is 0, so if you add a constant, then when you take the derivative, you just take the derivative of big F of x, that's little f of x, and then you add the derivative of c. But that's just the same thing as adding 0, right? You're adding a function whose derivative is 0. So if you have one antiderivative, you can always add or subtract an arbitrary constant, and that will give you other antiderivatives. So when we write this sign, we're kind of saying, don't just find me one antiderivative, find me all of them. And the way that you find all of them is by finding one and then saying, okay, I'm going to add an extra arbitrary constant. Okay? So the c represents an arbitrary constant. This is called an integral sign. It looks like a long S. That's actually because it comes from a sum. That's why there's an S. The S is for sum. You can define this using what's called a limit of Riemann sums. Not something we're going to do today, but the motivation for integration is kind of like taking a sum of infinitely many very small things. So for now, just maybe it's a nice little bit of trivia to know that the integral sign looks like an S. That's not an accident. That S is for sum. Okay. So let's just start with a few examples. Let's find antiderivatives for 5, 3x squared, and x squared plus 5. Okay, so we'll do this on a new page. Okay, so we're going to calculate, let me do it like this. Yeah, so we're going to calculate. So now I'm going to do this in 4 columns. Okay, so here we're going to have the integral of 5 dx. What was the other example? The integral of 3x squared dx, the integral of x squared dx, and the integral of x squared plus 5 dx. Okay. And when we're starting off with integration, all that we do is just guess, right? You're trying to find an antiderivative. You just at the beginning have to just guess. So, and maybe it's worth it to review the power rule. So maybe before we do these examples, let me just remember that we had 3 basic rules for differentiation. So we had this power rule for differentiation that if f of x was a polynomial x to the n, then the derivative was given by n x to the n minus 1. And then we had this addition subtraction rule that if f of x was equal to a sum or a difference of 2 functions, then the derivative was the sum or the difference of the derivatives. And then we had this constant multiplication rule. If f of x was equal to a constant times some other function, then the derivative is equal to the constant, same constant, times the derivative of that function. It's just to refresh your memory of how derivatives work. That's really all we're going to need for today. So now let's just guess. So we want to find a function whose derivative is 5. There's not really a procedure. You just have to figure it out and guess. So and I think through doing these examples, we'll remember how to guess. So anybody have a guess or an answer for give me a function whose derivative is 5? That's how we find the antiderivative, right? We're looking for a function that when you take the derivative, you get 5. Right? Anybody want to give an answer? Okay, well let me do it. I mean, so 5, one thing we can think of this also as you want a graph of a function whose slope is always 5. So what kind of yeah, James? Yeah, sorry. Uh, sorry, right. So what's a function whose slope is always 5? Well, that would be 5x, right? 5x plus c. I guess this is the answer. The integral of 5 dx, the antiderivative of 5 is 5x, right? Because 5x is a function whose derivative is 5, right? Yeah, 5x, exactly. So 5x plus c. And you can think of this as if I wanted to draw the graph of this, this is just a line with slope 5, right? Right? The slope is 5 everywhere. So the derivative of 5x is the slope of the tangent line. In this case, the tangent line just is the line. It's the same line. And so the derivative is 5. Okay? That's another one if you remember the power rule. So the derivative of 3x squared dx. Anybody just remember a function whose derivative is going to be 3x squared?
Yes, but
Yes.
Obus.
Question? Yep.
So if you're taking a antiderivative for 3x squared, we'll
Yep.
be having 3s squared plus 1 or 3.
Right. Right. So that's using the
And
rule.
then,
And what does that simplify to? If you were just trying to remember, what's that function that when I take the derivative of it, it just gives me 3x squared? So what do you get when you simplify that? Well, right. So when you simplify this, and I mean, so you're doing it systematically. You're using a formula for the power rule. That's great. But I think if you've been studying derivatives, especially if you've taken a lot of derivatives recently, we maybe haven't done it that recently because we just had one calculus session 3 weeks ago. But if you've been taking a lot of derivatives and your students have just had a unit on differentiation, you may just remember that, when I take the derivative of x cubed, I get 3x squared, right? Because remember, you just bring the 3 down and you get 3x squared. So x cubed is an antiderivative. And then, of course, plus c, you always have plus c. And this is a completely acceptable method for doing simple integration. Okay, so if you just remember, oh yeah, I remember some function whose derivative gives me this, then you just write it down, and that's the answer, right? So you see 3x squared, oh yeah, that's the derivative of x cubed. Okay, so the answer is x cubed. That'll work. So there's, again, not really any steps. You just say, oh yeah, I remember the derivative of x cubed is 3x squared. That works. Okay. So next question, okay, what about just x squared? Well, if the derivative of 3x squared is x, sorry, if the integral of 3x squared is x cubed, now we have x squared. This is 1/3 of this, right? The x squared is 1/3 of 3x squared. So its antiderivative should also be 1/3 of the antiderivative of 3x squared, right? If x cubed's derivative is going to be 3x squared, then if I multiply this by 1/3, the derivative will also get multiplied by 1/3, and that's good, right? Because that's going to give me, instead of 3x squared, that's going to give me x squared. So antiderivative here is going to be 1/3 x cubed plus c. Say because derivative of 1/3 x cubed is 1/3 times the derivative of x cubed. Right? So this is my kind of reasoning here. If I know that the derivative of x cubed is 3x squared, then the derivative of 1/3 x cubed has to be 1/3 of 3x squared, otherwise known as x squared. So I mean, we're going to figure out how to do this all systematically, but for now, this is we're just kind of reasoning. We're not doing anything in a rigorous way. We're just kind of guessing the answers. And if you take the derivative of this works. Pull down the 3, get 1/3 times 3x squared, and that's exactly x squared. So now what
So
about
I
this?
if I say
Sorry, James. Yeah.
so x x
Yeah. So do you want to do the last
cube.
one?
Well, I wonder every time you when you get there.
Yeah. So we're going to do the method. But do you want to just give the answer for the last one?
Then when you get there, I have no question there.
Question, yes.
Yeah,
What's the question?
let me
Yep.
try the last one.
So if I say x cube over 3 plus c, that should be correct.
Mm-hmm. Yeah. You could also
Okay.
write that as x cubed over 3 if you want to. That's fine.
Okay.
Yeah. That's
That's not complicated.
Yeah, it's the same thing. Okay, so for the last one, well, it looks complicated. We want to find something whose derivative is x squared plus 5. Maybe we don't know that off the top of our head, but we've already found something whose derivative was x squared. We found an antiderivative, that's 1/3 x cubed, and we also found an antiderivative of 5. That's 5x. So if we want to find something whose derivative is x squared plus 5, right? We can take something whose derivative is x squared and something else whose derivative is 5 and just add them together, right? So we have
Yeah.
an additive rule here. So all that we have to do here is just take the sums, right? So this is just going to be 1/3 x cubed plus 5x plus c, right? 1/3 x cubed plus 5x plus c. All that we have to do is take an antiderivative of one and take an antiderivative of the other, and then we can add them together, and it works. Okay, because when we take the derivative of this thing, remember, we're trying to figure out an antiderivative. When we take the derivative of this, what do? We take the derivative of this gives us the x squared, and then we take the derivative of this gives us the 5, and then we add them together. That's how derivatives work. You can do them term by term. And what that means is that for antiderivatives, you can also do them term by term, right? The derivatives work term by term. That means the antiderivatives. So if you have two parts, you can just do each of them separately. Okay, so any questions about these examples? I'll just say can do term by term. Okay. Okay. No question. Okay, so let's move on then. Okay, so how do we do this all systematically? Let's remember what are the actual rules that we use over here. So remember that for differentiation, oh, the graphs for the rest of the other examples, yeah, we can draw them, but I think the graphs shed a little less light in these other examples. So I mean, we can write them down. The graph of x cubed, let's say c is 0, is going to look kind of like this. We can put it on the axis. And this is what the graph of x cubed looks like. The graph of 1/3 x cubed looks, almost the same, just a little compressed. And then the graph of 1/3 x cubed plus 5x looks the same, but a little less compressed. And they all kind of look the same as each other. But I think for our purposes, these graphs don't really help us get the answer because it's hard to just look at a graph and say, oh yeah, the tangent line at x is always going to have slope x squared plus 5. For the first example, it might be a little helpful because I'm trying to say I want a graph whose slope is always 5. Well, what is that? That's just a line with slope 5. Okay, so for the first example, I think the graph is helpful. I think for the other examples, the graph is not actually so helpful. Doesn't really help you get the answer. But I mean, I can draw it if you want. Okay. All right, so what are our basic integration rules here? So recall from last time that we had these three basic rules for differentiation, right? The derivative of x to the n was n x to the n minus 1. You bring down the n, and then you lose 1 up here. If f was a sum or a difference of two functions, then to differentiate it, to find its derivative, you just differentiate each of the individual functions and add or subtract them. And if f was given by a constant times some other function, to differentiate it, you just differentiate the function and leave the constant along for the ride. Okay? And so what do we do on the previous slide? Well, implicitly, we used three basic anti-differentiation rules that parallel the corresponding rules for differentiation. So for anti-differentiation or for integration, we have three rules also. One is the power rule. If we want to find an antiderivative of x to the n, what it actually is it's x to the n plus 1 divided by n plus 1. So we did this on the previous slide where n was equal to 2, right? If n was equal to 2, this gave us x cubed over 3, right? Because n was equal to 2. This is what we had over here. We had integral of x squared. This gave us 1 x cubed over 3, or 1/3 x cubed. Same thing. Okay, so this is the power rule. Then we have an addition-subtraction rule, just like for derivatives. If f of x is g of x plus or minus h of x, then to integrate f of x, it's the same thing as integrating g and then adding or subtracting the integral of h. So again, you do the antiderivative step by step, term by term. And then lastly, if f of x is a constant times some other function, then to integrate or anti-differentiate f of x, you just, I left off a thing here. This should be c. There should be a c out here. Okay. So the integral of f of x is you just integrate g of x and you pull the constant out. Okay, so this is what we did before, where f of x in this case was 1/3 of something that we already knew the integral of. And now, what do? You just take that integral and multiply it by 1/3. Okay, thanks, Enoch. Okay. Okay, so the basic derivative rules work the same way for integrals, except that the power rule looks a little different. The power rule doesn't look like nx to the n minus 1. For the power rule, when you anti-differentiate, you have to raise the exponent by 1 and then divide by the new exponent. Okay. Okay, so these are these rules. So for instance, we can use these rules to just do some more complicated thing. You're not going to look at this and immediately know the integral, but if we want to do this systematically, I can say, okay, what's an antiderivative of 5x cubed minus 7x squared plus 3? Well, first I can just break it into its parts. That's just going to be the integral of 5x cubed minus the integral of 7x squared dx plus the integral of 3 dx, right? This is the addition and subtraction rule. And then I have all of these scalars, so I can pull them out. That's 5 times the integral of x cubed dx minus 7 times the integral of x squared dx plus, well, I'll just keep this as the integral of 3 dx. This is the scalar multiplication rule. And then lastly, we use the power rule. So from the power rule over here, right, the antiderivative of x cubed is x to the fourth divided by 4. Antiderivative of x squared is x cubed divided by 3. And then the antiderivative of 3, really, you can think of that as maybe I'll, just for overkill, I'll write this as 3 times the integral of x to the 0 dx, right? I mean, x to the 0 is just 1, so I'm just saying that's 3 times 1. And then this is going to give me 3 times x to the 1 over 1 plus c. I wouldn't usually write this. Usually we just know that the integral of 3 is 3x. That's a function whose derivative is 3. But since this is the first example we're doing, we'll keep it very, very, very explicit, right? We'll keep it very, very explicit. Okay, great. All right. Okay, so very, very, very explicit. Um, and now if I want to, I can just simplify this a little bit. So this is just going to be 5/4 x to the 4 minus 7/3 x cubed plus 3x plus c. Okay. Okay, so you have a polynomial like this. You can just always use these rules. Break it up into the terms, pull out all the constants, and then use the power rule to integrate. So this is, a pretty straightforward process. And it means that we don't any longer have to guess. I don't have to guess what's a function whose derivative is 5x cubed minus 7x squared plus 3. I can just do it systematically step by step. So this step is the power rule. Okay, any questions? Okay. All right, moving on. Okay, slightly more challenging example. Just going to be a disguised power rule. So what is the integral? What's an antiderivative of 1 over a fourth root of 16x cubed? Right? So you look at this, the expression looks a little bit complicated, but the
Yeah,
key is to just try to write this as something in a standard form that we can integrate. So yeah,
yes,
enough.
sir.
Mm-hmm.
Yeah,
Yeah.
this is very easy. So the first thing you need to do, you just need to manipulate using the law indices. First thing
Mm-hmm.
by expressing, yeah, because we know that we need to have something common to 16 and that of 4. So we just need to perform the algebra and flip the power. It tends to negative, then we perform our integration. That's all.
Okay, so so we want to just simplify this first. I'll just separate out the 16 and the x cubed, right? This is the first simplification step. Okay, so what do you want to do from here?
Yes, sir.
Yep.
Yeah, the next thing we know that we need to think what number we can raise to the full power to give us 16, which is 2. So the 2 to the 4 power cancel the root, so we just have 2 times that entire thing now.
Great.
Yes, so they just remain that way.
Right. So we know that the fourth root of 16 is 2. This is because 2 to the fourth power equals 16. Right. So here, instead of fourth root of 16, we can just write that as 2. Great. Okay. Next simplification.
Yeah, the next one is that we can bring, if we let, we can bring the 1 or 2 outside. Then
Okay.
we can write the entire power as x raised to the power 3 or 4.
Right. Okay. So let me do this. I'm going to bring the 1 over 2 to the outside. This is the constant rule. And then instead of fourth root of x cubed, we can rewrite that as x raised to the power 3 over 4. So I'm going to call this constant multiplication rule. Okay. And now we still need one more one more step before we can integrate.
Yeah, the next one is that we know that it will have 1 over a to the m. It can be written as a raised to the power negative m,
Right.
or m or n, whatever the case is. So we can write that entire thing as x to the power negative 3 by 4.
Exactly. Very good. So now we have this entire complicated expression here is now rewritten as just 1/2 times x to the negative 3 over 4. Right? And now we're finally in a position where we can use the power rule, right? Because this here is just x raised to some exponent, and that exponent is not -1. Okay, so for anything other than -1, you can always use the power rule. So now with power rule, okay, you want to finish it up? So we have to add 1 to the exponent here. So we have -3/4 plus 1 is equal to 1/4, right? So that's x to the 1/4 divided by 1/4, right? This is because -3/4 plus 1 is equal to 1/4, right? Okay, and this is maybe I'll say power rule.
Man, you got us.
Okay. Okay, right? So now that we had to do all these simplifications to get this into the form where we could use the power rule, but now we can just use the power rule, right? And so we add 1, and so it's x to the exponent 1 higher divided by that same exponent. And now if we want to simplify a little bit further, dividing by 1/4 is the same as multiplying by 4 over 1 times times x to the 1/4. I'm just inverting and multiplying. Now plus c since I did the integration. And this simplifies to 2x to the 1/4 plus c. Okay, so it may look a little complicated, but all you need to do is simplify it until you can use the 3 rules that are our most basic integration rules. So there's 3 rules. In this case, we didn't even need to use the addition or subtraction rule. We just needed constant multiplication rule. We could pull out a constant, and then the power rule, once we could write whatever was inside here as an actual power of x. Okay, any questions about this one? Okay, let's move on. Okay, so these were indefinite integrals. The real applications of integration always come with definite integrals. Okay, so let me define that. So the book kind of starts off with this, but I think now we've built up to it where this definition makes sense. So if f is a continuous function on a closed interval a to b, then we say that the definite integral of f from a to b is written as the integral sign of f of x dx, but we put a little a at the bottom here and a little b at the top here. And that's what we're going to call the definite integral. Okay, and how do we evaluate it? Well, so that you can evaluate this integral, what do? It's just like a standard integral. You take the antiderivative, but instead of just leaving that as a function, You plug in b and you plug in a and you subtract. So you find this antiderivative and then you do f of b minus f of a with the antiderivative. And I should mention that the fact that you can define a definite integral this way is the fundamental theorem of calculus, okay? It's not really the definition. The definition is given by a limit of so-called Riemann sums, and that's motivated by approximating the area under the graph of f of x between x equals a and x equals b by rectangles. I don't want to go into details of this here, but you'll see a little bit of this on pages 588 to 590 of the textbook if you want to look it up. But basically, you should think of the definite integral as, by definition, it means the area under the graph of f of x between a and b. But what is the method where you evaluate it? You evaluate it by finding an antiderivative and then doing this subtraction. It's just kind of like the derivative. The derivative, the definition, is in terms of a limit, giving you a slope of a tangent line. But the method is usually to use the power rule and use these other rules. You don't usually use the limit when you're evaluating the derivative. So same thing here. The actual definition of this is some kind of limit, but what you want to actually do to evaluate it is by finding antiderivatives. And what you should notice is that when you evaluate a definite integral, this thing is calculating an area, right? This is supposed to be calculating the area under the graph of x between x equals a and x equals b. And so that means that your answer when you evaluate a definite integral should be a number, not a function, right? When you do an antiderivative indefinite integral, you're just getting a function, right? You're getting 2x to the 1/4 plus c. But when we do a definite integral, we're plugging in numbers to get an area. So our answer should be a number. Okay, so this is what we mean by a definite integral. It'll make much more sense when we just do an example. So let me do a basic example. So example 1, we're going to integrate from this is read the integral from 0 to 4 of 3x dx. And we're going to interpret this as the area of a triangle. So let me just do the first part. So integral from 0 to 4 of 3x dx. Well, we know for calculating this, we can pull out a 3. So I get 3 times the integral from 0 to 4 of x dx, because I can always move scalars out. And now
Yes.
we use the power rule. Sorry, let me just do this one just for speed, because I want to get to some of the other things. So for the power rule, we get that the integral of x is going to be x squared divided by 2, right? Because this x is really x to the 1. So when we do it by the power rule, we raise the exponent by 1 and divide by the same number. And now the notation that we use here is I draw a line and I write 0 to 4. I'm going to say here that you don't need a c for definite integrals. Okay, and that's going to be because if you had a c, it would end up getting subtracted off anyway. And what this symbol means is it means that you're going to first plug in 4, and then you're going to plug in 0, and you're going to subtract. So the red stuff you don't write, but this is what it actually means. So what is this? This is 3 times 4 squared over 2 minus 3 times 0 squared over 2. And if you calculate this out and do the math, as James has mentioned, this comes out to be 24. Okay? So that turns out to be 24. Okay, so now I want to interpret this as the area of a triangle. So let me draw this graph. Right? So let me draw the graph y equals 3x. Okay, so let me draw. If this is the graph y equals 3x, this is my x-axis, this is my y-axis. If I'm going to integrate this from 0 to 4, what that means is between 0 and 4, I want to figure out this area. Right? I want to figure out this area. The integral from 0 to 4 of 3x dx is exactly the area under the graph between x equals 0 and x equals 4. And we know we can calculate this by doing antiderivatives. But in this case, this is just a triangle, right? So if I have y equals 3x and x is equal to 4, then my y value here is 12. So what I have is a triangle whose base is 4 and whose height is 12. And so we get that the area is equal to 1/2 times the base times the height, and this is also equal to 24. Okay, so we see that this integral that we get from doing antiderivatives and using the fundamental theorem of calculus, in this case, it's a shape whose area we can evaluate anyway, right? And so when we just evaluate the area of the shape, it comes out to be 24, just like what we had before. Okay, because this is just telling you the area under this graph, but since it's a straight line, the area under the graph between 0 and 4 is just the area of a triangle. Okay, and so for an area of a triangle, it's easy to evaluate, just 1/2 times the base times the height. Okay, any questions on this? Yeah, right. So it involves, right, the first, you can do it directly with calculus, but if you wanted to, you could also do it with geometry, and it will get you the same answer. The advantage of calculus is that calculus allows you to do problems that are too hard to do with geometry. So if this is just some nasty function, you're not going to be able to solve the area using geometry. The only way you'll be able to solve it is by using calculus. Okay, geometry is not going to work. But in this case, it works, and so it's nice to see that you get the same answer. Okay. I think we have time for one more example. So yeah, I'm going to skip the next example, but you can do that for homework. Yeah, okay. So this is the last example we'll do for time. So find the area bounded by the x-axis, the line x equals 0, the line x equals 1, and the graph of y equals x plus 1 times x plus 2. So let me try to draw this region. So I'm only going to draw the first quadrant because that's all that we'll need. So we have the x-axis. We have the line x equals 0. That's just the y-axis. Here I have x equals 1. That's going to be this line right here. Let me redraw that line. 1, that's going to be just this line. Okay. And now I have the graph of y equals x plus 1, x plus 2. It's maybe not so important to know exactly what that graph looks like, but at x equals 0, that's going to give me 2, and at x equals 1, that's going to give me 2 times 3. It's going to go up to 6. So it's going to look something like this. Yeah, sorry. Okay, then the area is going to look something like this. Okay. This is not going to be something that we could do very easily using geometry because this is some kind of quadratic function. So instead, we're just going to have to use calculus. And so to do this with calculus, well, we're looking at an area between x equals 0 and 1. So that's the integral from 0 to 1 between the x-axis and some function. So that's x plus 1 times x plus 2 dx. Now, again, this is not in a form that we can work with just yet, right? Because this is not, you don't have a product rule for integrals. You have something called integration by parts, but it's not as simple as just saying take an antiderivative of x plus 1 and take an antiderivative of x plus 2 and multiply them. That just doesn't work. That works for addition, but it doesn't work for multiplication. So the only thing that you can do here is just first you have to expand. So x plus 1 times x plus 2, you just have to write that as x squared plus, then we have 1x and 2x, so that's going to give us 3x, and then 1 times 2 gives us 2. So you just have to expand this out. Okay, well, we're going to finish up in the next 5 or 10 minutes, so you won't miss too much. This is the last example we're going to do. Okay, and now the rest of this is standard integration, so let me just go through it. This is integral from 0 to 1 of x squared plus 3 times the integral from 0 to 1 of x plus the integral from 0 to 1 of 2. I'll write dx is here for everything, dx. And now we can use our power rule. This is going to be x cubed over 3 evaluated from 0 to 1 plus 3 times x squared over 2 evaluated from 0 to 1. And then the integral of 2 is 2x evaluated from 0 to 1. And again, we don't need any constants because it's a definite integral. And now as a shortcut, it's going to turn out that when we plug in 0 for any of these things, they all go to 0, right? So we're going to plug in 1 and plug in 0, and then we're going to plug in 1 and we're going to plug in 0. But this really ends up just being equal to 1 cubed over 3 minus 3 times 1 squared over 2, and then plus 2 times 1. The 0, I'm going to say plugging in 0 always gives 0 here. So we only need to worry about what happens when you plug in 1. That gives us 1 cubed over 3 minus 3 times 1 squared over 2. Plus 3 times 1 squared over 2. And then plus 2 times 1. And I'm just going to do that in my head. That's a third plus 3 halves, which is 11 sixths. And then plus 2 is going to be 23 sixths. Okay. So that's going to be the answer here. I mean, you can work it out if you want it. I mean, this, I assume everybody can just do on their own. So if you don't believe me, you can work out the details yourself here. But this is what you're going to get. Okay, yeah, the 3.83 in decimals. Good. So that's the area. So here you just have an area. There's really two parts. So I'll just say the first part is write as a definite integral. Okay. The second part is this is not a form that you can do the integration in, so you have to expand, first of all, x squared plus 3x plus 2, and then once you have that as a polynomial, now you can just go and use the rules. Okay, and use the rules by using the power rule and the addition rule and the scalar multiplication rule. Okay, so we're more or less out of time. So let me just go finish up. Here's another example. So a trickier example combining integration with algebra. So I'm just going to leave this as an exercise. You can do it and send it to the chat if you want. It'll be in the notes that I send out. So find b such that the integral from 0 to b of x to the fourth is equal to 25. So it's a kind of odd looking problem, but I claim that you know enough to do it. So you can try it. But let's not talk more about this one. And then there's a ton of exercises in the textbook, which are also good to study. I don't like how the textbook talks about the meaning of definite integration, but it does do very well with exercises and examples. So the exercises in the textbook are good to study. And of course, if you're responsible for teaching this material, you'll certainly be more effective if you can do all of the exercises in that chapter of the textbook. So just to recap, what did we do? We motivated the study of antiderivatives. We learned some intuition for the fundamental theorem of calculus. We learned some formulas for evaluating antiderivatives. We evaluated several definite and indefinite integrals using the formulas, and then we calculated areas using the fundamental theorem of calculus. Okay, so not bad in a day's work. And this is really at the high school level, this is the extent of the calculus that you need to do, that you need to know, right? There's not time to do any more than this. At the university level, one can do more. But in terms of the high school material, these are the main things that you want to be able to do. But I think even at the high school level, even though there's no way this is really tested on the WAS or anything, I think you will be a more effective teacher for calculus if you know kind of what the fundamental theorem of calculus is and you have some sense of why it works. Okay, so let's finish with that. And so I'll say next week, we'll meet next week. That's April 23rd. And we're done with the mini workshops now. So we're going to begin training sessions for the WITS math competition and the WAS. Okay, so some of you are maybe coaches for the WITS math competition, and others of you may be coaches in the future. So I want to talk a little bit in particular about this competition and look at some sample problems. And we'll do some training for, how to approach this with your students. Okay, so we'll have 2 sessions for this. All right, so as always, thank you for your attention. If you haven't written your name down yet in the chat, please do so because I'll stop the recording soon. And then, I will see you next week. Any last questions or comments? Okay, I think everybody who's here wrote down their name. So I'm going to stop the recording.